Hello, I am Manohar. Today I am going to present the project AI for cooking. Let's first understand the problem statement. AI-based scheduling in hostel kitchen. A hostel kitchen prepares multiple types of meals for a large number of people. It can be like veg, non-veg, Jain, etc. Each meal consists of several food items, example rice, sabji, paneer, chicken, etc. Each food item is prepared using a sequence of subtasks, example clean, cut, boil, which have dependencies represented using a direct, directed acyclic graph. In directed acyclic graph, there will be a node which represents a subtask. Each node in the DAG is a cooking related operation like cleaning vegetables, cutting items, boiling, frying, etc. Each subtask node contains operation ID which is denoted by PI, unique identifier which is used to track and possibly match similar tasks across food items. Resources required, which is denoted by RI1, RI2, so on. The tools or applicants needed for this subtask. Examples: knife, which is represented like R3, stove, which is represented to R2, like etc. Execution time and batch size. Example: 10 minutes 50 people means it takes 10 minutes to process a batch of 50. Edge, which represents dependency. An edge from node A to B means subtask B cannot begin until subtask A is completed. For example, cutting vegetables, P2 must be done after cleaning P1. This helps maintain the correct order of operations, prevent resource conflicts or logical errors. Characteristics of DAG in this problem: multiple sources. Example, multiple ingredients start their own subtask like onions, potatoes, paneer. Merging paths. Different branches may converge when a common task or operation is needed later. Shared operations. Two or more food items can share subtasks with the same operation ID. Example, cutting potatoes for sabji and chicken. These can be executed once and reused in multiple DAGs. Execution implications. Tasks can be parallelized across batches and cooks. If resources are available, dependencies are resolved. You must schedule carefully to avoid bottlenecks. Example, multiple tasks needed stove R2 at the same time. Ensure no cook or resource is overcooked. Let's see execution rules. Like first is like batch execution. Each subtask is designed to serve a fixed batch. Example, 50 or 100 people. You can split large groups into smaller manageable batches. Next is parallel execution. If enough cooks and resources are available, same task, example, frying F5 for two batches, can run in parallel. Multiple subtasks can run simultaneously provided dependencies are resolved. Task sharing. Common subtasks between multiple food items. Example, cutting potatoes for sabji and chicken need to be done only once. Reuse improves efficiency and avoids duplication. Challenges in scheduling: limited resources. Tools like stove or pan may be required by multiple tasks. Limited cooks. Every subtask needs at least one cook. Dependency management must represent the DAG's order. Load balancing. Avoid overloading a few cooks while others are idle. Constraints. We'll see. Like first one is like fixed number of cooks. You are given a predefined number of cooks in the kitchen. Each cook is versatile. They are capable of handling any subtask, cleaning, cutting, boiling, etc. However, the total number of cooks is limited, so not all subtasks can run in parallel unless enough cooks are available. Load balancing is important to prevent overburdening some cooks while others are idle. The scheduling algorithm must assign at least one cook per subtask, distribute tasks to ensure no idle time, and efficient multitasking. Next, fixed number of resources. Resources include like knives, stoves, etc. These are shared across all food items and all subtasks. If two tasks require the same resources, they cannot be executed simultaneously unless there are multiple units of that resource. The scheduler must check for resource conflicts. Example, two tasks needing the same pan. Resource availability at the given time. Efficient resource reuse and minimal waiting time. Each subtask must have at least one cook. No task can proceed without manual intervention. At least one cook must be allocated to every subtask. Even if tasks are small or fast, they cannot be skipped or automated. This ensures human supervision or execution for safety and quality. Avoidance of resource wastage or unintended process. The goal of this project is to design a AI-based scheduler that minimizes the total completion time of all food preparations, ensures balanced workload among cooks, efficiently manages shared resources and task dependencies. This problem can be solved with the algorithm like A star and using SAT solvers and genetic algorithms. Thank you.
Hello everyone, my name is Ranjit Kumar and I am presenting AI for cooking, and in particular the subtopic is genetic algorithm. So overview of the genetic algorithm. A genetic algorithm is a search and optimization technique that mimics the process of natural selection, survival of the fittest. It works by evolving a particular population of candidate solutions over several generations to find the best one. Think of it as Darwinian evolution applied to problem solving. Overview of genetic algorithm process. Initialize a population, evaluate a fitness, selection, crossover, mutation, replace slash form next generation, repeat until stopping criteria. Overview of the genetic algorithm. First one, it contains initial population. We have to create an initial population of chromosomes, that is possible solution. Each chromosome is usually represented as a string like binary form 101010 or a list of numbers. For example, if you are trying to optimize a function f of x, your chromosome might be a float value x. Second, fitness function. Every chromosome is evaluated using a fitness function. This function tells us how good a solution is. For example, for maximizing f of x equal to x squared, the fitness could be a value of x squared. Third, selection. Chromosomes with higher fitness are more likely to be selected as parents. Chromosome selection methods. Rowlett-Wills selection, that is fitness proportionate. Tournament selection, pick the best one out of a random group. Rank selection, sort by fitness and select probability. Crossover, recombination. Mimics biological reproduction. Two parents combine to create one or more children. Types. Single point crossover chooses a crossover point and swap tails. Parent 1 contain 110/011. Parent 2 101/100. Child will contain both the quantities of the parent 110100. 2-point crossover, uniform crossover, etc. Mutation. Randomly flip or change a part of chromosome to maintain genetic diversity. Prevents the algorithm from getting stuck in local optima. For example, original is 110011 and mutated is 111011 and bit is flipped. Next, forming the next generation. Combine parents and children or just children to form the next population. Sometimes a mix of elitism, keeping the best individuals, is used to preserve strong solutions. 7. Stopping criteria. The loop repeats until one of these happens. A solution reaches a desired fitness level. A maximum number of generations is reached. No significant improvement over time. So real world example in function optimization, the goal is to assign a f of x equal to x times sine 10 pi x plus 1, where x is in the domain of 0 to 1. The chromosome float value of x and the fitness value of f of x, population, list of random x values, selection, pick best x values, crossover, average over two values, mutation, add small random noise to x. Over time, the algorithm evolves x value that gives the highest output for f of x. These are some of the applications of genetic algorithm. Genetic algorithms is particularly used in traveling salesman's problem, feature selection in machine learning, game strategy optimization, evolving neural networks weights, resource scheduling and allocation, art and music generation. Advantages: works well with nonlinear, multimodal, and discrete search spaces. Doesn't require derivatives or gradients. Can escape local minima. Disadvantages: can be computationally expensive. More coverage slowly. Doesn't guarantee finding the global optimum. This is the generic genetic algorithm with a pseudocode. First one, we have to initialize a population P with n individuals, that is random solution. Second, evaluate fitness of each individual in population P. Repeat until stopping condition is met. Selection. Select a pair of individuals from a population P based on fitness. Crossover. For each pair, apply crossover to produce offspring. Mutation. Apply mutation to offspring with a small probability. Evaluate a fitness of each offspring. Create a new population. Option 1. Replace entire population with new offspring. Option 2. Combine parents and offspring. Then select top end. Then update population P with the new individuals. Then after that, finally return the best individual that is found solution. Thank you.
Hello everyone, I'm Anubhav Kant, and from here I shall be proceeding with the heuristic approach which we have applied in our project AI for cooking. So firstly we should shall discuss what is A star search. A star search is an informed search algorithm that always chooses the path that seems most promising. It uses a cost plus estimate formula. Here, GN represents the cost so far. It is also the actual cost from the node to reach the goal node. And HN represents the estimated cost to reach the goal node from a particular node. And the FN represents the total estimated cost of reaching the goal through the node N. It guarantees optimality if our heuristic that we have chosen is admissible. So we have designed a domain specific heuristic function for our project. It is given like this expression. Here the R are set of remaining tasks, T denotes the time, and I denotes each of the subtasks, C denotes the number of cooks, D denotes the set of final dishes already partially completed, Q denotes the quantity required of dish J, and AJ represents the available amount of dish. Here J represents the dishes. And we have named the second term as gift. It rewards the states which are closer towards the goal. So in our project, we have applied the heuristic function with this logic. Here, firstly, we have calculated the time required for all the remaining tasks. We have summed up all the time required, and then we have distributed this workload among all the available cooks. And in this step 3, we have rewarded the states that already have required outcomes prepared. And now we shall be discussing AI algorithm in our project. So we shall be discussing the key components involved in our project. First key component is state. State represents the current schedule, outcomes, remaining tasks, cook timers, and equipment usage. Actions denotes the actions are the valid combination of moves of a task to free cooks. And transitions, and in transition we shall be transitioning from one particular state to other, and we shall be updating time, outcomes, and freeing up the cooks. Here we shall be either freeing up the cooks or making the cooks occupied with a certain subtask. And here we have here is the logic of the pseudocode of the A star search algorithm. Here is the open list, and while the list is not empty, we shall be updating the current from the best state from the open list. We shall be okay. And here, if the current state is goal state, then we shall be returning the current. And for each valid task, for each valid task combination, we shall be assigning task and move it towards the next state. And during this process, we shall be advancing the time and update outcomes. We shall be computing the heuristic then, and then we shall be adding the new node to the open list. So we shall be proceeding with a very simple example uh, for checking for witnessing how our heuristic and A star algorithm is working. So suppose we have resources like this. We have cooks available as 5, and we have equipments R1 to R10 available with us. And they are in varying amount of availability, as you can see here. And suppose our initial ingredients are as follows, and we have the goal to prepare the final dishes like this. Suppose we have a particular dish which is encoded as 1000 here, and its quantity is 50, and all of the dishes as also the same quantity for our example. And now suppose we have example subtask. It is an excerpt from all the subtasks present in our input.dg file. As you can see here, note down the time here. We shall be proceeding with the calculations. So here is our heuristic function comes in action. So suppose there are remaining tasks like we have to cut the vegetables, boil, marinate, fry, cook, and we have to mix them. So all these tasks, subtasks will take the total time as 60 minutes, and we have five cooks. So we shall be dividing them by the 60 by 5. So our heuristic function measures as 12 here. Now we assume suppose we assume some progress. We suppose that or we have already made 25 units of dish 1000. Actually our target was 50, but we have made 25. So our gift would be 50 divided by 25 into 2. It shall be equals to minus 4. Why we have added minus? Because when we have already prepared the dishes, it shall not be proceeding with them again. So we have reduced our reward here, gift term here. And now here the final heuristic will be as follows. Uh, it is given shall be given by 12 minus 4 equals to 8. So here is our summary of the results. Advantages of heuristic A star. It incorporates the food cook availability and equipment constraints, and it is balancing the load across all the cooks, and it prioritizes useful intermediate outcomes via the gift factor. And we have our results as it produces a near optimal schedule, and it outperforms the brute force or other uninformed search algorithms in terms of speed and scalability. Thank you.
Hello everyone, I am Harsraj. In this video, we will cover the motivation behind using SAT for scheduling, outline the overall approach and encoding of each constraint, and then wrap up with the objective formulation and solver comparison. First, why go down the SAT route? Many scheduling problems are naturally stated as CSPs, and by encoding a CSP as Boolean satisfiability problem, we leverage powerful SAT solvers that excel at exploring huge combinational spaces using Boolean logic. This approach lets us model complex relationships such as task precedence, resource limits as logical clauses which can be difficult otherwise. The solution pipeline consists of 6 steps. First step, parse DAG file has main task to read the recipes as .dag file, to extract subtasks and other set as shown in code snippet. Then we unroll the subtasks to determine how many times each subtask must run to meet output requirements. This generates new IDs for each batch of subtasks and also adjusts batch size. Once subtasks are unrolled, we initialize the CP SAT model, time unit, and a global time horizon H, which here we have used as sum of time units of each task. This horizon actually affects number of variables and constraint, so we need to carefully define its value. Now we have constraints. Here we encode the heart of scheduling rules, task precedence, cooks, capacity and equipment number into Boolean clauses. Then objective is defined. We will see constraint and objective in detail in further slides. After constraint and objective definition, we finally call solver to get SAT solution and print the solution. Now we will see mathematical formulation of constraint and their code implementation. So first, we define our variables, which are start and end time of each unrolled task. And there is also interval variable for each task, which essentially gets entangled with start and end time due to model.newIntervalVar. This is one of exclusive features of our tools. Now, due to model.newIntervalVar earlier, first constraint has already been added. For precedence constraint, we make start time of any task equal or more than end time of any of its condition tasks. For cook constraint, we use model.add cumulative, which essentially at most k encoding, ensuring at most k cooks can work in one time interval. Similarly, for equipment constraint, we ensure at most some n equipment is used in an interval where n is different for each equipment as given in input DAG. Now to define objective function, we introduce a makespan variable m. This is done by ensuring m is greater than n time of all tasks. Now for objective function, we minimize m alongside all constraint to get minimum time of schedule, which is also valid. Now we will see some comparison between our tools Z3 solver and other SAT solver. From table we can see main difference lies in ability of our tools, which have exact way of encoding and solving scheduling constraints efficiently in comparison to Z3, which is more general purpose solver, and other sort solvers mostly lack optimization functions, making them useless for optimization. So now we conclude with the knowledge of why SAT encoding is very useful, why our tools are best for scheduling, and most importantly, how each constraint is translated into Boolean logic for scheduling. Thank you everyone.